Hi, welcome back. This is Professor Ridge and today's lesson on section 1.4, equations of lines and modeling. So in section 1.3 we talked about the slope-intercept form of a line, as a linear function. So y equals mx plus b, or if we use function notation, f of x equals mx plus b, where m equals the slope and 0b is the y-intercept. So if I asked you to find the line, find the equation of a line, okay, so the slope's negative 3/4 and the y-intercept 0.5. Now this is the easiest of all these type of problems to do, where you're asked to find the equation of a line. So if I just straight tell you, okay, the slope is negative 3/4, so you just put it where the m is. So remember, it's mx plus b. And then the b is the y-coordinate of the y-intercept. So 0.5 is y-intercept, so 5 is b. So we put plus 5, and you're done. There's really no work to do. Okay, now a little harder would be find the equation of the line. Find the equation of the line. Okay, so a little bit harder is I give you a point that's on the line, so like 2, 3, and the slope is 5. So we start out with the y equals mx plus b, plug in what we know, slope is 5, x is 2, y is 3, from the point 2, 3, it's an x and a y, plus b, and then you solve it for b. Subtract 10, so b is negative 7. So once you know what b is, now it's just like the first example. I have a slope, which is 5, and I know what my b is, which is negative 7. So that my answer would be y equals 5x minus 7. Okay, we could do this problem an alternate way using the point-slope equation, which is just y minus y1 equals m times the quantity x minus x1. So let me show you the same example using slope-intercept form. So I'm going to write m equals 5, and the point is 2, 3. Goes through 2, 3. So I'm going to do y minus y1 equals 5x minus x1. Now, there's no instruction saying write the equation in slope-intercept form. I'm done. Oops. No, I'm not. I got to write 2 here. Now I'm done. But typically we put it in slope-intercept form, so you're going to distribute the 5. So you get y minus 3 equals 5x minus 10, and then you want to get y by itself, and you get the same equation we got above. Okay, so it doesn't matter to me which technique you use. You can write the slope-intercept form of the equation, plug in what you're given, solve for b, or you can use the point-slope equation, point-slope form. Alright, so either one would work. It's up to you how you want to do it. Okay, now this one's a little bit harder because instead of giving you the slope, I'm just giving you 2 points. So the easiest is I'll give you a slope and a y-intercept, pretty much know where to do. And I give the little bit harder, be a slope and a point. And then a little bit harder is I just give you 2 points. So our first step we got to figure out slope. So in all three cases, we need to know the slope, we need to know the y-intercept. So my first step is figure out the slope. Remember, m equals y2 minus y1 over, it's rise over run. So y2 minus y1 over x2 minus x1. And if we call this one the first point, x1, y1, x2, y2. So we're going to get negative 5 minus 7 over negative 1 minus a negative 3, which is negative 12 over 2. So my slope is negative 6. So now I have slope is negative 6, and I can just pick either point, doesn't matter which one. So I'm going to use whichever technique you want. It doesn't matter to me. I kind of flip-flop between both techniques. So I'll use the slope point form because I got a slope and a point, so I'm going to use slope point form. Y1 would be 7, m is negative 6 that we just figured out. X1 is negative 3, so minus a minus 3 becomes plus 3. Then I'm going to distribute the 6, the negative 6, and then I'm going to add the 7. And I get y equals negative 6x minus 11. And I'm done. Okay, so that was a little bit harder. Alright, so parallel lines are two lines that, in geometry, you say two lines that never intersect, so that would be an example of parallel lines. And in algebra, we define it to say, well, if the two lines are vertical lines are parallel, right? So that's given. And then non-vertical lines are parallel if and only if. Now, so this means that this rule goes both directions. If the lines are parallel, then they have the same slope. If they have the same slope, the lines are parallel. Now notice here it says non-vertical lines are parallel if and only if they have the same slope and different y-intercepts. Okay, so that part's just added so that you get two different lines, two unique lines. And again, the non-vertical, because if it's a vertical line, the slope is non-existent, right? It's undefined. So you can't, so we had to treat vertical lines separately, right? So that's what that's about. So basically, two lines are parallel if their slopes are equal. Perpendicular lines, two lines with slopes m1 and m2 are perpendicular if and only if the product of their slopes is negative 1. So that's the test is you multiply the slopes. If it's negative 1, then they're perpendicular. So let me give you an example. So if I had a line that had slope 3/2, then the perpendicular slope would be you flip it over and change the sign, because 3/2 times to get negative 1, I have to do the reciprocal, and it's the negative reciprocal to get negative 1. Right, so I'm going to flip it over and change the sign, so that's down 2, to the right 3, and that'll give me a perpendicular line. So m2 equals negative 2/3. Alright, so that's the test is you multiply the slopes. If it equals negative 1, it's perpendicular. If it's perpendicular, so again, it's an if and only if statement, so it works both directions. If it's perpendicular, then the product slopes is -1. Product slopes is -1, then it's perpendicular. Okay, so we have to treat the horizontal and vertical line separately, because if the horizontal line is 0, 0 times anything is 0, so that would cause a problem. And then the vertical line, the slope is there isn't any slope, it's undefined. So that causes a problem too. So again, we just talked about it separately. So if you have one vertical line and one horizontal line, they're perpendicular. Okay, so determine if lines are parallel or perpendicular or neither. So again, to be parallel, you have to say M1 equals M2. Well, -3 does not equal -3 does not equal -1/3. So not parallel. And then to be perpendicular, M1 times M2 has to be -1. So let's test it. -3 times -1/3, that equals +1, which is not -1. So it's not perpendicular. So we'd say neither. Okay, so when we do modeling and curve fitting, so we want to fit a curve to a data set. Of course, we have what's called linear functions that we're studying in this section. So linear function is a line. We also have a quadratic function, which we know is a parabola. So it might be something like that. And then we have cubic function, which might be something like that. We could have any of the different functions we studied. This one we haven't really studied yet. It was at the end of Math 90, if you recall. So exponential function could be something like this. So what we do is we do a scatter plot, and you want to see if it fits what model you're going to use, whether you use a linear function, quadratic, cubic. So all the things that are not linear, quadratic, cubic, exponential, you can have a square root function, all the other. So the only thing that's linear is a graph that makes a line. Everything else is nonlinear. So these are nonlinear. Okay, so linear is the line, everything else is nonlinear. Okay, so what we do is, if we're going to take our data and we're going to make a scatter plot. So if you go out and collect data and you start putting dots wherever, and you start plotting, and you're going to have a few strays maybe, but if the overall trend becomes a line, this kind of suggests that, that it may not, but it looks like it's a linear function. So that might suggest a linear function. If you have something that looks like, you start plotting the points and it looks like and that's not linear or non-linear. Right, so that's you can kind of see whether the relationship suggests a linear relationship or not, based on the scatter. There's this fancy term called a correlation value, correlation coefficient, and it will tell you based on, the closer to your 1 the closer it's to 1, the better correlation is to the linear relationship. Okay, I'm not going to worry about getting into all that. You can use the technology for it. If you were to take a statistics class, we'd get into it pretty deeply. All I care about for this class is you just understand. You make a scatter plot. You can tell, just get a feel. Yeah, it kind of looks linear, or no, it doesn't. And if it is linear, then the way you're going to model it is you just pick 2 points on this line that kind of best fits it. And again, there's a precise formula. It's called a linear regression. And you can find the best fit line, but we're not going to get into that deeply. You just find a line that looks good, get 2 points on that line, and then find the equation through those 2 points. So that's all I want to say about that. Okay, so I'm going to make a scatter plot. Okay, so let's do an example. Data on the median age of the U.S. population and selected years are listed in the table. Model data with a linear function, estimate the median age. And now, since they tell me to use a linear function, I really don't have to do the scatter plot. I can just pick 2 points and draw the line through it, right? Or find the equation line through those 2 points. I just kind of want to give you a feel of the whole process. So we do a scatter point, 0 and 30.2. Now this mark here, saying, hey, I truncated scale. See, this is not, I'm going to start here at 28 and I'm going by 2. So that kind of distorts the image a little bit. So 0, 30.2, which will probably be right about there. 10, 29.5, right about there. 20 and 28, 30 and 30, 40 and 32.8, and 50 and 35.3. And 58, 36.8, which is right about there. Now, it is good to draw the scatter plot because I probably wouldn't use this point, and maybe I will. I kind of like these. Kind of like this point and this point. So I'm going to use what point was that? 40. Well, actually I'm off a little bit. Close enough. 40 and 32.8. And I'm going to use 60, 58, and 36.8. Okay, so my m is going to be y2 minus y1, x2 minus x1, which is 36.8 minus 32.8, over 58 minus 40, which equals 4 over 18, which is 2/9. Alright, so now I'm going to put in, well, let's make it a decimal. Well, that'd be 0.2222. And since we're kind of roughly estimating anyway, we'll just round it to 0.22. Okay, it's 0.222 with a line above it, but we'll just round it 2 places. So y equals 0.22x plus b. Got to figure out my b. So let's put in the 40 and the 32.8. And solve it for b. So let's see, that's going to be, is it 880 or 8? Yeah, so it'll be 888.8. And then I'm going to subtract 8.8. So B is, so what's that, 34, 24. So my equation is going to be y equals 0.22 x plus 24. Or I should say f of x, right? That doesn't matter. Now use this line to estimate use this function to estimate in 1978. So 78 would be, so 50 is 0, so 78 would be 28. So I'm going to write it up here. So we got f of x equals 0.22x plus 24. So 1978, I'm going to plug in 28. And punch that in my calculator. And I get 30.16. Okay, which seems about reasonable because 78 is close to 80, and you see the median age was 30. So we'd get different answers depending on which points that we used. But I'm comfortable with that one. And now let's use this this function to predict 2020. So that's 70 because 1950 is 0. So we plug in 70 plus 24, and we get 0.22 times 70 is 1.54, or 15.4. So it's 39.4. Okay, so that answers that question. And that concludes the lesson for 1.4. Go to my math lab, complete your exercise there, and I'll see you in class.